2.5, really more of the same, except more words. More words. The value V, we're keeping it linear, but there are more words that we have to deal with. The value V of a tractor purchased for $14,000 and depreciated linearly at the rate of $1,400 per year is actually given to us. I would have expected to have had to maybe find that on our own, but it was given to us. Great. Thank you. Find the value of the tractor after 2 years. And when will the tractor have no value? According to this linear depreciation that's done here. All right. I don't know. This problem may not feel like a very satisfying way to end up such a stimulating class period. But we'll do it nonetheless. It's not going to stress us out. At least there's that. Find the value of the tractor after 2 years. I'm thinking that's V of t. Time is t, and that's measured in years. So if what's V of 0? What's V of 0? When we first purchased it, $14,000. You plug in 0 for t, you get $14,000. 2 years later, evidently it's losing what, 10% of its original value every year, so it's losing $1,400 a year. So we're going to basically subtract $1,400 from this twice. And so V of t is whatever negative $2,800 plus $14,000 is. What is the value after 2 years? Calculator time maybe. Second, quit. 14. Uh-oh. So $11,200. Did I do that right? Something like that. $11,200. And the other one that may challenge us a little bit more. When will the value of the tractor be 0? So it's actually asking us to find the 0 of this function. V of t, I should say. V of t, when? When will that happen? So negative 1,400t plus 14,000 equals 0. Well, if it's losing 10% of its original value every year, how long is it going to take to get to 0? 10 years, right? That sounds right. So I think that's what's going on here. If we divide both sides by 1,400, or negative 1,400, t does equal 10, and it is years. Something I should mention, I'll ask several times next time. We're going to be looking for an interpretation of the slope of this line. What is the slope of this line? It is negative 1,400. And what is that negative 1,400 telling us is happening to the value of this tractor? It's decreased. The value of the tractor is decreasing by $1,400 each year, right? So that would be the interpretation of this slope. Wonderful. Have a fantastic day and Friday and weekend and everything else. Okay. The daily cost to manufacture 100 printers is $11,000, and one would seem to think that we could figure out the cost per printer simply by dividing, but it probably some fixed costs that have nothing to do with the actual number of printers that are manufactured. Cost of keeping the lights on, cost of paying the folks to do it, regardless of how many printers that they manufacture. A lot of costs. But if 100 printers, if that's a level of production, it's $11,000. If, on the other hand, it's 145 printers per day being manufactured, that's $13,250. So we want to express the cost as a function of the number of printers. It depends on other things that evidently are fixed but we want to express it as a function of the number of printers that are produced in a day. So let's, I guess x would make sense for a variable there. So let x be the, number of printers produced daily, manufactured daily. And not really going to set up an equation so much as I believe to find the slope. We want to assume here a linear model. It's in the entire section we're looking at linear models, so it doesn't specifically say linear here. Probably should have. If I put this problem on the test, I probably should say something like construct a linear function which expresses the cost as a function of the number of printers. But with that, what we have is two data points. We've got 100 printers, $11,000, and we also have, let me scoot it over so I can label them. We also have 145 printers, $13,250. Be careful not to have too many commas there. So I'm going to suggest that we find the slope of the straight line that goes through these two data points. And then we use the point slope form of the equation of the line to write an equation of the straight line that goes through these two data points, and use that as our way of expressing the cost as a function of the number of printers. So if we want to call this x sub 1 and y sub 1, and x sub 2 and y sub 2, we could use the slope formula to find the slope. M equals $13,250 minus $11,000 divided by 145 printers minus 100 printers. And these application problems, the linear application problems that involve slope, we want to keep in mind the units that are involved in the numerator. We've got dollars up in the numerator. And the units that are involved in the denominator, we've got printers down in the denominator. So when we write the slope, and let's see what it's going to be. If I do the subtraction there, I'm thinking $2,250 divided by 45 printers, and where's my calculator? There it is. $2,250 divided by 45 printers is how many? How much? 50? Really? Just 50? I guess it is. 50. And I'm going to scoot over just a little bit. There we go. I guess I have just a smidge less horizontal space, but I just, I could have made do with that. $50 per printer. When I write it in the actual function, I may not put all that verbiage in there. I might just go with 50. But that's the slope of this straight line that goes through these two data points. If we're thinking about a graph, along the x-axis, we have printers. X printers. And I'm thinking, well, we've got 100 and 145, so maybe 50 printers might be manufactured, or 100 printers, or 150 printers, something like that. On the y-axis, we've got dollars. Dollars there. Daily cost. Daily cost. So probably $5,000, and $10,000, and $15,000 might be reasonable numbers to put. Might have gone 5, 10, 15. It just said it's in thousands, but that is what it is there. 111,000 would be about right there. So that's one of the data points that we have been given. And 145, $13,250. Something like right there. So those are our two data points, and there's a straight line. I don't know, the y-intercept might be $5,000, but it looks like it's in the neighborhood of that. this is a partial graph of the function that expresses the daily cost in terms of how many printers are manufactured. So we want to give it a name. Let's call it C of x. C of x equals, we don't have our function yet, do we? We've got the slope. Point slope form is the next item on our list. So I'm pretty sure that the directions specified to do that, let's see. Nope, didn't. Got to keep going. 6,000. I sneaked a peek at it. Looks like the y-intercept is actually 6,000. Now let's see if I can get there. Not ready to write the function yet. I've got to use the point slope form. Recall y minus y sub 1 equals m times x minus x sub 1 is the point slope form of the equation of a straight line. So y minus, we have two data points. Anybody have a preference which one we use? X sub 1, y sub 1, since it's already conveniently labeled x sub 1, y sub 1. So y minus $11,000 equals $50 per printer. I'll go ahead and put the dollar sign by the $50, but I'm not mentioning printers anywhere else. If I wrote out, well, printers is kind of embedded in the y there, so we'll just keep in mind it's $50 per printer. But we'll say x minus, I suppose if I were going to write the word printers next to the 100 there, then per printer might have made sense to put up underneath the $50, but I'm not. So here's an equation of the line. We just need the slope-intercept form of this equation. So when we pick up the y and replace it with c of x, it'll look like a linear function. So to put it in slope-intercept form, simplify just a little bit. What do we have? Y minus $11,000 equals $50 times x minus $5,000. Add $11,000 to both sides. And we get y equals $50 times x plus, whatever you get when you combine those, $6,000. That's an equation of the straight line that goes through those 2 points. If we pick up the y, replace it with c of x, that will be the daily cost function of manufacturing these printers. So $50 times x plus $6,000. Then the follow-up question. So we've got our function. That was everything for part 1 or part A, however I labeled that. Then we get the follow-up questions. Interpret the y-intercept. Spoiler alert. What do you suppose the y-intercept is? Fixed cost. It's not dependent on how many printers we manufacture each day. Basically, the cost of bringing everybody to work, turning the lights on, paying the lease on the plant or the mortgage, loan, whatever. Insurance, everything that goes into keeping the place going, which we're going to have to pay anyway, even if we don't manufacture the first printer. Okay, that's the fixed cost. It doesn't depend on the number of printers that we manufacture. Interpret the slope. What do you suppose the slope is? $50 per printer, those were the units. So if we're at a certain production level and we increase that by 1 printer per day, it's going to increase our production cost by $50 per day. So it's the cost for manufacturing the next printer. If we subtract the $6,000, what do we have there? One of our data points was $11,000. So if we subtract that fixed cost from that, we get $5,000. Am I doing that right? It's early in the morning. $11,000 minus $6,000, $5,000. We manufactured 100 printers for that $5,000. So $50 a printer. It's the amount it costs it's cost per printer, but it's the amount it's going to increase our daily cost if we increase production by 1 printer per day. How many printers were manufactured if costs were $11,500? Well, we've got an equation to solve. This is the hard one. This is one that for which there was no spoiler, I guess. If C of X equals $11,500, that wasn't one of the data points, was it? No, that's in between somewhere. Well, what? That's $500 more than it cost when we were manufacturing 100 printers. So how many more printers could we manufacture for that $500? 10 more. So it's probably going to be 110 printers. Would that make sense? Manufacture 100 printers at a particular level and increase that by $500. You should increase the number of printers that you can manufacture by 10. But let's go ahead and show our work here. $50 times X plus $6,000 equals $11,500. Subtract $6,000 from both sides. And so the actual cost that's going into manufacturing those printers is $5,500. And we divide that by 50. So $5,500 divided by 50. And look at what's going on with the units here, because I actually could include the units in this case. $5,500 divided by $50 per printer. That's what we're actually dividing by. We're not dividing just by $50. We're dividing by $50 per printer, because that's what the slope represents. It's the cost per printer. And so if we do this, the dollars divide out. So there's not a dollar sign in the question, and the answer to the question, how many printers? There's no dollar sign there. But there is printers. If you're in the denominator of the denominator, you're actually in the numerator. So X equals 50, if I could just do the arithmetic here, what do we say, 110? 110 printers. There. So key questions, and look for questions like this on the test. Interpret the y-intercept. Put together some sort of intelligible sentence. The y-intercept represents the fixed cost. You can elaborate. You could say it's independent of the number of printers manufactured, something like that. Or you could just say fixed cost. Those would be key words that I'd be looking for there, fixed cost. Interpret the slope. You want to say it's something per something. That's what slope represents. It's a rate of change. Generally, it's expressed as a ratio, something per something. Just look at your slope. Look at what are the units in the numerator. Maybe it's dollars. What are the units in the denominator? Maybe it's printers. And if you say it's the dollars per printer, that's going to go a long way toward getting full credit for that. So just look at the units along the y-axis, units along the x-axis, and do the division there. Dollars per printer, and that's going to be what I'm looking for. All right, good. Let's see. Example 3 is more of the same. I'm thinking it's going to seem disturbingly redundant. Cost of producing 4 modems, cost of producing 10 modems. It's worked out. Let me see if example 4 is going to give us something new and exciting. Well, maybe none of the above, but it's necessary nonetheless. Parallel and perpendicular lines. There are situations where we have two quantities and they're experiencing the same rate of change, but maybe different, for example, fixed costs. The relationship between parallel lines, the slopes would be the same. Perpendicular lines, the slopes obviously are not the same. In fact, the slopes don't even have the same sign. What is the relationship between slopes of perpendicular lines? Anybody know this from another algebra class somewhere? So take the reciprocal, do the opposite sign. So the opposites of each other is reciprocal, basically, is the relationship between slopes of parallel lines. So slopes of perpendicular lines, rather. So let's look at example 4 and see if we can determine whether the indicated lines are parallel, perpendicular, or maybe neither. Lines 1 and line 2, how much easier could it be if they're both in slope-intercept form? It goes a long way toward determining whether the two lines are parallel, perpendicular, or neither if we can identify the slopes. So what is the slope of this top line, L1 here? We'll say M1 equals -2. And the slope of the bottom line? It's also -2. Now, it's necessary for two lines to be parallel that they have exactly the same slope. It's not quite enough, but almost. If we have two equations of lines and they have the same slope, they will be parallel provided what? They're not. They're what? They don't have the same y-intercept. Because if they had the same slope and the same y-intercept, they'd be the same line. And a line's not parallel to itself. So they have to have the same slope, but there has to be something different about them. They can't be the same line. The y-intercepts being different is enough to say these lines are parallel. Just like that. Now, a lot more work has to be done with the B part because we've got to figure out what their slopes are. My suggestion would be solve them both for y. Put them in slope-intercept form, and then we'll be able to tell. So it looks like if we solve the top one for y, we have, I'm just going to copy and paste it over here, and then subtract x from both sides. 2y equals -x plus 9. Divide both sides by 2. And y equals, do I need to throw in one more step maybe, just to be on the safe side? Y equals -x over 2 plus 9 over 2. And if we take x and multiply by -1 and divide by 2, that's equivalent to multiplying x by -1/2. Is that believable? -1/2 times x is the same thing as -1 times x divided by 2 plus 9/2, or 4.5. We'll go with 9/2. So the slope of the first line is -1/2. And the second line, add 8x to both sides to get 4y equals 8x minus 1. Divide both sides by 4. So y equals 8x divided by 4 minus 1 over 4. Y equals x minus, whoa, what's 8 divided by 4? 2. So 2x minus 1/4. And so the slope of line 2 is 2. Do the two lines have the same slope? No. 2 and -1/2, in fact, are the opposites of each other's reciprocals. They have opposite signs and their absolute values. 2 and 1/2 are reciprocals of each other. So this would be an example of two lines that are perpendicular. We know they're not the same line if they don't have the same slope, so we don't have to even consider their y-intercepts. If their slopes are the opposites of each other's reciprocals, these lines are perpendicular. It might be useful to sketch their graphs, but I think you can visualize what we mean by two lines being perpendicular. They intersect at a 90-degree angle, form actually 4 90-degree angles there at the point of intersection. And the C part, I suppose that we would have to exercise just a little bit of caution here. If we find the two slopes and find that they're the same, we'd probably need to do a little bit more. I mean, we could just find the equation of each line. We've got plenty of information to find the equation of each line, and if we confirm they have the same slope and different y-intercepts, that would confirm that they are parallel. If we find the slopes of each line and find their opposite reciprocals, that'd be enough to say that they're perpendicular. Maybe we won't have to work that hard. Top line, M1 equals, if I'm calling this x sub 1, y sub 1, x sub 2, y sub 2, -1 minus 7 over 8 minus -9. Let's work downward here. M sub 1 equals negative 8 over 17. It's kind of an unexpected slope, but it looks like that's correct. Negative 8/17 for the slope. What's going on for M2? If I call this one x sub 1, y sub 1, and x sub 2, y sub 2, M sub 2 would be 10 minus negative 7 over 14 minus 6. Well, how about that? 17 over 8. Are they parallel? They're perpendicular. Yes, their slopes are the opposites of each other's reciprocals, and so these are perpendicular lines. No further analysis needed. Good. So we have the slope formula, and we have the point slope form for finding equations of a straight line. If a problem wants us to find an equation of a line, as this one does, first thing we should do is start looking for a point and a slope. When it says find the equation of the line, my suggestion would be write down the point slope form, y minus y sub 1 equals m times x minus x sub 1. And once we find a point and the slope, then we can substitute that information into this equation, put it in slope-intercept form, and we have the equation that we need. What we're told is the equation we're looking for, the line that we're looking for is parallel to y equals negative 3x plus 1 and passes through the point 2, negative 3. All right. So evidently, there's only one line that does that. I'm not going to be all that careful here. Y equals negative 3x plus 1. I'm thinking looks something like that maybe. Has a negative slope, kind of steep. 3 down, 1 to the right, 3 down, 1 to the right. There is a line, there are lots of lines that go through the point 2, negative 3. Darn it! That point is so darn close to the line. Is it above the line or below the line? I really don't know. I don't know what side of the line that point's on. Never mind the picture. How are we going to find the slope of the line that we're looking for if all we know is that it's parallel to this line?
It's the same slope.
It's the same slope. It's the same slope as this line since it's parallel to this line. And what's the slope of this line? Negative 3. So the line we're looking for has a slope of negative 3. And the line we're looking for passes through the point 2, negative 3. The point 2, negative 3 is not on this line, is it?
No.
How would we tell that?
Which line?
So negative, it's not on this line whose equation is given. Negative 3 times 2 is negative 6, and negative 6 plus 1 is negative 5. Close to it, but not quite. So let's go with y minus negative 3 equals negative 3 times x minus 2. My apologies for the excessive number of negative 3's in this particular example. But there they are. One for the y coordinate of the y of the point that's given, the other one for the slope. Y plus 3 equals negative 3x plus 6. And subtract 3 from both sides. Y equals negative 3x plus 3. So two lines, based on how steep they both are and how close their y-intercepts are together, very close together, but evidently the point 2, negative 3 is just above this line. If this is the line, I don't know, would that pass for a line with a slope of 3? That's maybe even steeper than 3. Neither one of those looks like a line. Anyway, y equals negative 3x plus 3. Disappointing example. Let's see if the perpendicular line goes a little bit better. Find the equation of the line that's perpendicular to the line with equation 4x plus 3y equals 1. It goes to the point 1, 5. If we substitute 1 for x and 5 for y, do we get anything close to 1? I don't think so. 4 times 1 is 4, 3 times 5 is 15, and 4 plus 15 is maybe about 19. So this point should not be terribly close to this line. So let's see if this goes any better at all in the visual. Maybe. So a line 4x plus 3y equals 1. So I'm going to go with 1 right there. And let's see if I can come up with this, the line. The x-intercept is 1/4. The y-intercept is 1/3. So I'm thinking the line looks something like the line that's given looks something like that. We're going to say that's 4x plus 3y equals 1. The line we're looking for, perpendicular to this, it goes to the point 1, 5. So 1, 2, 3, 4, 5. 1, 5, about right there. So what would a line that's perpendicular to that look like? Maybe something like that. Yeah, I think that would pass for a perpendicular line. So the red line is the one we're looking for. If only we knew the slope of the blue line. How are we going to find the slope of the blue line? Put in slope-intercept form. Subtract 4x, subtract 4x. 3y equals negative 4x plus 1. Divide both sides by 3. Y equals negative 4x over 3 plus 1 over 3. Multiplying by negative 4, then dividing by 3 is equivalent to multiplying by negative 4/3. So negative 4/3 x plus 3, so that is the slope of the blue line. Therefore, the slope of the red line, maybe call it M perp. Slope of the perpendicular line is what? 3/4. Change the sign, take the reciprocal, and get 3/4. So we know the point is 1, 5, and we know the slope is 3/4. That's enough information to write an equation for that line. So y minus 5 equals 3/4 times x minus 1. Y minus 5 equals 3/4 x minus 3/4. And the not so nice y-intercept, I guess that's okay though. Add 5 to both sides. And y equals 3/4 x. Alex is probably not going to like a mixed fraction. Might be okay with a decimal, although I wouldn't try it. If we subtract 3/4 from 5, that's 4 and 1/4. 17/4. 3/4 x plus 17/4. Yep, that looks like about 1, 2, 3, 4, and 1/4 right there for the y-intercept. So decent picture, way better picture for this one than for the previous one. Hard problem or easy problem? Step by step. We're not asking if it's if it's fun, which is it terrifying? That's the question. Well, terrifying might be fun in some circumstances, I guess. Linear regression. I do not think Alex has any problems to enable you to practice linear regression. If need be, I think I could produce maybe a GeoGebra worksheet. I'll put a link to it on my webpage that you can click on and practice this topic. I would like to put it on your test. I think it's an interesting topic. It's one that we probably would not do if we weren't spending $100 anyway on the graphing calculator. But since we have the graphing calculator for other unrelated reasons, it's I think an excellent example of an application of a linear relationship between two quantities. So I want to go ahead and do this for this example and for the test. Notice the way the example is numbered. Looks like a bunch of examples were skipped. I copied this and pasted out of previous notes without renumbering the examples. But just want to keep in mind that Alex is not going to give you practice problems, so if it's a little bit fuzzy and you would like some practice problems, I would need to provide those for you separately. Let's look and see what the problem is asking us. I hope you have your calculator handy for this one. Put it over here. Following data were collected to determine the relationship between X, the number of chirps per minute, I'll refer to this as the chirping frequency, of the male snowy tree cricket, and Y, the temperature in degrees Fahrenheit. So we've got degrees Fahrenheit versus chirping frequency. So evidently, somebody with a stopwatch and a thermometer and way too much time on their hands went out somewhere where snowy tree crickets were in abundance and counted chirps. How many chirps per minute? So when the temperature, I can imagine maybe it happening in the cool of the evening. The temperature was 67 degrees, maybe not all that cool. Some serious chirping there, 110 chirps per minute. Imagine what that might sound like. As it cooled to 56 degrees, the chirping frequency diminished significantly to 65 chirps per minute. And then it got really cool. 44 degrees, the chirping frequency was all the way down to 20 chirps per minute. So what we want to do is plot these points using the calculator and look and see if it looks like there's anything close to a straight line. Now, if we were to plot the points, and we've got, let's see, Y represents temperature in degrees Fahrenheit, and X represents chirping frequency. If we were to plot these points, and they were just all over the place, like in a case like this where it's really cold and not much chirping going on, and then we wait and it's still cold, but then there's a whole lot of chirping going on. And then on the other hand, it's really warm, but not much chirping, and then it's still warm, and then a whole lot of chirping. We would think there's really the chirping frequency and the temperature really don't have a whole lot to do with each other. One doesn't really determine the other because these dots are just all over the place. On the other hand, if we were to look and see something like, we started when it was warm, there's a whole lot of chirping going on, and then it began to cool and there's less chirping, and it cooled some more and there's less chirping, and it cooled some more and there's less chirping. And if we start to see kind of a trend where there's a linear relationship between temperature and chirping frequency, then maybe it makes sense to come up with the equation of a straight line to model this phenomenon. So I'm going to put this into the calculator to see what we get. So to get there, let's see where to begin. First, I'd like to get the calculator to draw a picture of it. So it's a dangerous thing to do because it can induce some very, very frustrating invalid dimension errors. So you're going to have to remember before we dismiss today, we're going to turn this. Whatever did I? Yeah, I moved the taskbar, so that wouldn't happen. Maybe if I'm right-handed, maybe the taskbar should be on the left. Would that make sense? Anyway, There's the calculator. So what we want to do is second stat plot. Y equals. On the Y equals button, if you press the second button and then right up above it, Y equals, it'll take you to this menu. Second, and then up to Y equals. That stat plot, press the number 1. And we just want to make sure we're looking at the same thing. So second button, Y equals button, number 1 to adjust this. And press enter for on to turn the stat plot on. And then several different types there, unless you're taking statistics or so you've got the calculator for somebody that's taking statistics. Probably it's set to the correct scatter diagram mode. There's some other ones there, some frequency histogram and box and whisker plots and all kind of good stuff there. But we don't want that. We just want the scatter diagram. We would like the X coordinates, the X values looking at the L1 list, where we're going to put them, and the Y list looking at L2. If yours is yours is pointing somewhere else other than L1 or L2? Is that what it says? Because we can adjust it, but if nobody needs to, that's fine. I like to leave the mark at a square, because what we're going to do is plot the points, have the calculator plot the points, and then have the calculator graph a line. And if we just go with a dot, it might cover up the dot and we'll forget where the dot was. So the square is good, so it draws the line, but we still remember where the point was. Okay, if we're good with those settings, press the second button and the button immediately to the right of it, the mode button, which has the word quit up above. So second mode or second quit, back to the main screen. Now we want to input our data. To do that, we press stat. There we go. The edit menu number 1 on the list. Edit, press 1. Oh, we've got a lot of numbers here. Let's see. If necessary, press the left arrow until it goes to the L1 list, and just verify with me that you see an L1 list and an L2 list. Hopefully they're both clear. Are they both clear? Now, if they're not clear, if there's data that you want to save somewhere, you could store that in a different list. Otherwise, careful about how you do this. You want to avoid pressing the delete button. When you're down here, you can get rid of those by pressing the delete button. But in general, it's dangerous to press the delete button. So I don't know if I'd encourage you to do that. To clear a list, press the up arrow until it's highlighted on the L1, and then press the clear button again, not the delete button. Clear button. And then it looks like nothing happened, but then if you follow that with the down, it will clear the list for you. And then press the right arrow and then the up arrow if you need to clear the L2 list, and press clear. And then the down arrow, like that. Now, if you slip up and your cursor's on the L1 or L2 and you press delete instead, the list just goes away. And then panic ensues. Because my list is gone, how do I get the list back? Well, if deleting it gets rid of it, insert will get it back. So you press the second button, I think I pressed the second button, followed by the delete with INS up above it. That will insert the list there. And it goes and it puts a spot for it. And then down here on the number 3, in blue or yellow up above that, you see L3. So you can press second L3 and press enter, and it'll put it back together with whatever data was in it. So let's type in these numbers. L1 is going to hold our X coordinates. So type 20 and 40 and so on. You can press enter each time, and it will go down to the next value. I've just got 7 data points so that they'll all fit and we can see them all at once. Of course, they'll hold, I think these lists hold up to 999 data points, but I've just got 7 here. And then the Y coordinates, type it in, press enter each time. There we go. Hopefully they are correct. Up there. All right. Now I just want to get the calculator to draw a picture. On the test, I'm not going to ask you to get your calculator to draw the picture. So it will not be necessary to use the stat plot feature. So when we turn the stat plots off at the end of class before we leave today, it will not be necessary to turn them back on. But stat plot is on now. So let's just press Y equals and see if you have any equations there. You might have some equations. If those aren't near and dear to your heart, you might just want to clear each one of those. Clear, down, clear. There we go. Because they'll get in the way of our picture possibly. If I just press zoom 6, zoom 6, I should now see nothing at all. Because if you remember our data points, not one of these is in the viewing window where x is between negative 10 and 10 and y is between negative 10 and 10. The least x coordinate is 20 here and the least y coordinate is 44, so these are way up in the first quadrant. So I don't want this viewing window, but with the stat plot turned on, if you press zoom, got to move my taskbar, not that. What did I do? If you press zoom 9, if the stat plot is turned on and you've got the data in your L1 and L2 list, it will automatically set your x min and your x max and your y min and your y max to fit all these points comfortably on the screen. Yes. Did it do it? Did it not do it? It did not do it. Let me get a quick look at that. We'll leave it rolling and see what we got.
My stat may not be turned on, but
Zoom 9 just gave you nothing. Yeah, let's see if it's turned on. Let's see. There's a kind of a fast way to turn it on. There you go. All right. So we're looking at the points. Now, we could go in now and press window. I'm just going to press the window button. And you can see what zoom stat did. It automatically set the x min to 11 and the x max to 119, the y min to 40, and the y max to 70. Now, if you like to see the x axis on your screen, you can set the y min to 0. And if you like to see the y axis, you can set the x min to 0. And if you don't like the x axis and y axis cluttered with tick marks, you can change the x scale to 10 and the y scale to 10 and press graph, and then I think it kind of shoves it up toward the top of the screen here. Yeah, but at least you can see the x-axis and y-axis and see what's going on. You've got on the x-axis, what's that? Chirping frequency, 20 chirps per minute, 30 chirps per minute, 40 chirps per minute, 50 chirps per minute. On the y-axis, it's 10 degrees, 20 degrees, 30 degrees, 40 degrees, 50 degrees, 60 degrees, and then 70 degrees. So we can kind of see what's going on. Does it look like there's a linear relationship between the temperature and the chirping frequency based on the limited amount of data that have been collected here? Yeah, it kind of looks like there is. So what we're going to do is get the calculator to come up with the equation of the line that comes as close as possible to as many of these points as possible. Now, there's a kind of a sophisticated procedure that the calculator is going to go through to do that. We don't have to worry ourselves with the details of that. But basically, it's going to come up with a straight line. And let me copy and paste this so I can manipulate that a little bit. It's going to come up with the equation of the straight line that something like that, that minimizes. I keep. Is that what I keep hitting? Maybe it is. That minimizes the sum of the squares of the vertical distances between these points and the straight line. Well, how does the calculator do it? We want to press second button followed by the stat button. No, we don't. It's been a while since I've done this. Let's try again. Let's just press the stat button. Okay, I've got it now. So you press the stat button, and then you press the right arrow. Gee whiz. I must be hitting it with the base of my palm. That's got to be what it is. And I think the problem is that the calculator is way over there. So we press the stat button, we press the right arrow, and then what we want is number 4 on the list, the linear regression equation. Now down below the bottom of this screen, down below that quartic regression, there's another linear regression of the form a plus bx, but we don't want that one. We want the one that's going to give us a number a, which is going to tell us the slope of the line, and a number b, which is going to tell us the y-intercept of the line. So linear regression of the form ax plus b, press enter. Now, it may be, if you're using a TI-83 plus, probably all you have to do is press enter one more time. By default, the calculator should be looking at the L1 and the L2 list, and if you press enter one more time, it should go ahead and find this. Calculator just making sure. You sure the x coordinates are in the L1 list? Yes. Sure the y coordinates in the L2 list? Yes. Frequency list. I don't think I want a frequency list. I think I just want to clear that. What does yours say for the frequency list?
It's blank.
It's blank. So yeah, I think I want to clear that. And I really don't want to store it. If I wanted to graph it automatically rather than manually, I might want to store it. I just want to calculate it. And it does. The A is the slope. I'm going to round that to 0.25. The B is the y-intercept. I'm going to round that to 39.52. The R squared in the R is the correlation coefficient. Yours, by default, might not have given you the R. Might not have given. If you feel like you're getting shortchanged, and you still have memories of that check that you wrote to get this calculator at the beginning of the semester and would like to get your money's worth, I can show you how to get the R. To get the R, you press the second button, followed by the catalog button. The catalog button's on the 0. So if you press second 0, and then press the down arrow a bunch of times until you get to something that starts with the letter D. There are the A's, the B's, the C's, the Chi's, some more C's, and more C's. We want D. We want diagnostic on. I know. Diagnostic on. Press diagnostic on and then press it again. Press enter again. And it looks like nothing happened. But if you repeat the process, stat, right arrow, 4, calculate, or just enter on the TI-83 plus, it should give you the R squared of the R at that point. Once your diagnostic is on. Now, the R is the correlation coefficient. If it's linear regression, the kind that we just did, that number is going to be between -1 and +1. If it's positive, it means, as it is in this case, if it's positive, it means there's a positive correlation between the two numbers. Might be really strong or it might be really weak. If it's negative, it just means the slope of that line is negative. If it's close to 1, it means there's a really strong positive correlation, and this one is ridiculously close to 1, the correlation coefficient is. So it means these lines are virtually collinear. It's basically what it's telling us, and looking at the picture we can tell that. All I'm going to ask you for on the test is the equation of this straight line. Y equals 0.25x plus 39.52. That's what I'm looking for here, for the equation of the straight line that comes as close as possible to as many of these points as possible.
So we don't need the R. No?
Don't need the R. If the R were close to 0, it would just mean that the points are all over the place, and it doesn't look like there's any straight line that really even comes close to modeling this situation. If the R is close to 1, it means there's a really strong linear relationship between them. The B part. A couple of follow-up questions here. going to grab our equation, copy it and paste it down here as well, up in the corner. If 80 chirps are counted in 1 minute, what is the approximate temperature? Well, I think we're having to extrapolate a little bit. If we have a set of data and it gave us, say, a number that's in between the least and the greatest, if it gave us this number and wanted to know, well, what's the point on the graph that has that number as its x-coordinate, and we're just kind of looking for the coordinates of that point, that's called interpolating, figuring out what's going on in between existing data points. But it told us 80 chirps per minute. And then, let's see, where is our chirping frequency? That's the x-axis, right? 10, 20, 30, 40. Is that the x-axis or the y-axis? Y-axis is temperature. 80 chirps in 1 minute. No, that's within our bounds. Because we've got 65 chirps per minute there, 90 chirps per minute. What's your best guess as to what the temperature would be? 50, 58, 59, 60 degrees, something like that? If there's a linear relationship here and the chirping frequency is in between there, I would guess the temperature is in between there somewhere. So this is not extrapolating. It's actually, this is a meaningful sort of thing to do. Y equals 0.25 times 80 chirps per minute plus 39.52. Y equals 20. I believe that's the fourth of 80, plus 39.52. So y equals 59.52. Now, you might find a little bit of information on this topic if you Google the word terpometer. Okay, a way of actually measuring temperature by counting cricket chirps. But even if you successfully are able to estimate the temperature, I don't know that you want to express it to the nearest hundredth of a degree. I mean, there's some thermometers that might be more accurate than others, but if you're using a chirpometer, I would think if you could get it within a few degrees, you should feel really good about yourself. So let's call it 60 degrees Fahrenheit. On the other hand, if the temperature is 70 degrees Fahrenheit, how many chirps per minute? I think this might be extrapolating a little bit because the highest temperature data point we had was 67. So we're going to expect more than 110 chirps per minute, but that's pushing the envelope just a little bit. So we would substitute 70 for y. Y represents temperature, equals 0.25x plus 39.52. Subtract 39.52 from both sides. It's a linear equation. We can solve this. I hope we can. What's that? 30 point something? 30.48 maybe? Equals 0.25x. So x is whatever 30.48 divided by 0.25 is. And how much is that? 121.92? 0.92? Okay. So what? I guess go ahead and call it 122 chirps per minute. There we go. Round to the nearest chirp per minute. Yeah. All right. Now, before we forget, if you've got your calculator, let me show you the fastest way to turn off the stat plot. See, later what you're probably going to do on the test is you're going to be, did I actually have the calculator graph this? 0.25, we plotted the points, but what if we graphed a straight line? 0.25x plus 39.52. There's a way to get the calculator to store that in the Y1 automatically, but I don't want to take the time to do that. Just type it in, 0.25x plus 39.52. If we press graph at that point, does a pretty good job of getting as close as possible to as many of these points as possible. Different slope, different y-intercept, probably going to miss some of the points by more than it misses them by. Now, let's turn the stat plot off. See, later what's going to happen is somehow these lists are going to get cleared. I mean, you might have something like that, and you go to graph something, and you see this happening. This will happen to somebody in this room. Okay, look to the left, look to the right. This will happen to somebody that you're looking at, and it will cause needless frustration. Fastest way to fix this dreaded invalid dimension error, or there's another one, dimension mismatch. That's another one that sometimes happens. Let me see if I can get it to do a dimension mismatch. If there's actually something stat, and if there's something there, and I try to press graph, yeah, there it is. The dimension mismatch error. Same sort of thing, same cause. The calculator is trying to plot points that aren't there. It's got an x-coordinate of 40 and there's no y-coordinate to go with it. Or it's got x-coordinates and no y-coordinates at all in the L2 list. And so the fastest way to fix this is to press the y equals and press the up where it's flashing on the plot 1. If you just press enter and turn that stat plot off like that, that way the calculator is no longer trying to plot points that aren't there. So let's just all do that together. Press the y equals, press the up arrow, press enter, turn the stat plot off, and then when we press graph, doesn't plot our points that aren't there, but it will graph a straight line, and you can use this to solve equations graphically and that sort of thing. And you can avoid the very, very frustrating dimension mismatch error and invalid dimension error. All right, yes. What's that? To turn it off, just to turn the stat plot off, y equals, and plot 1 should be highlighted, emboldened, however you say that. Just press the up arrow till it's flashing on plot 1. Press enter, and I just turned mine back on. So go up there, press enter while it's flashing on that, and press the down arrow again, and now the stat plot should be off. And you should not have to worry about this. And I'm not going to ask you to plot those user calculator to plot the points on the test, so there should be no need for you to turn the stat plot back on. Let's just leave it off. Don't have to worry about the dimension mismatch error.